Maybe. Okay. Slightly off. Does it work? Doesn't work. Okay. In case where it is slightly off from positive definite case, calculator work, but quality does not work. Okay. So if it is positive definite, calculator should work. If it is a little bit off from positive definite, calculator can still work. Because I tried and it worked. Okay, last one, SOR. Successive over relaxation. Did you do this code in Excel yet?
Yeah.
Naturally. Jerlin, you did? Any problem? Is that just fine? Ami?
Fine, yeah.
Josh Furthermore? Daniel? Please do it before getting 0. Alright, SOR. SOR is a weighted between new and old method. Okay. When omega equal to 1, you go toward outside I think. So this time I have class SOR answer. So I have SOR method. SOR method is put whatever you guys did, but in the coding format. If you want to know how it works, you follow the step. When I run it, it works just fine.
Why did you create a class for this?
What?
Why did you create a class for this one?
Oh, okay. I want to do something like, when I get the answer, I want my answer to be able to do something like this. Answer.x, and it tells blah blah blah, answer dot something. Let's take a look at the class a little bit. When I have class, I have self.x, self.sse, self.I, self.div. Okay, that is SOR answer. That is the class of SOR answer. Do you use it anywhere? Here? Look. Return object of the type SOR answer. And that object is S, SSE, I, div. So my return object, my return value is not tuple, is not like list or anything, it's object. So when I return it as an object, if you do .x, you get the x value. I mean from x equal to b, you get the solution. If you do .sse, you get some square error. If you do the .I, you know how many iterations. If you do the div, you know how much is the difference between XO and XNew. Just that. Just to show you how to make it a little bit more organized. You don't need to do this. Alright. And it's just correct. Okay, let's take a look at this graph a little bit. This is a graph where we change omega. Okay. Cannot use my mouse, but x-axis is omega, y-axis is the number of iterations. If you adjust omega poorly, it takes a lot of iterations until it converges. Okay? Like if my omega is too small, if my omega is too big, it takes too many iterations. So optimum, by adjusting omega, you reach your solution faster, more efficient. That's the point of SOR. Okay? Sometimes omega equal to 1 is not best. So you may have to adjust it a little bit, depending on what type of problem you have. Okay, Thomas algorithm. You will use this, you create a function of this. So I create tridiagonal matrix. 6 minus 1 minus 2. Okay? And I show you two ways of creating it. Method number 1, I create it manually. You just follow. Okay? Method number 2, pay attention to this. You need it for homework. diax. Okay, and diagonal equal to ABC, and then comma offset minus 1, 0, 1. So minus 1 it means it go to bottom, I think. So you see A equal to minus 1, B equal to 6. Offset of B is 0, so 6 stay in the middle. Offset of minus 1 is A is minus 1, so minus 1 stay here. Offset of C, which is 2, 2 stay, minus 2 stay on the top. So this is how you can quickly create diagonal matrix. If you want it in the star matrix, doesn't show you anything. It's an efficient method to store the matrix. But if you want to make it in the like user-friendly format, you do dot to dense. It gives you n by n form. Okay. So why do we use sp.spa.diax? Because it's more efficient. When you have a big matrix, a lot of zero, you don't want to store zero, right? You don't want to use your memory to store zero. You want to store the location that you have number, right? That's for spa matrix. A2.data give me whatever data that I have. Okay, one thing to look at is sometimes it's added zero. Yes, question. Go on. Sometimes A2.data is not with 0. A2 of minus 1 is add with 0. So it may not be something that you expect. So you always check A2.data. A2.offset, this gives me the offset. A2.data 0 give me the first list, which has 0 at the back. See? How about this one? A3 to sp.sparse.add bracket 40 multiplied by 6, comma, this comprehension, minus 1 multiply I for I in range 1, comma 6, comma, range minus 20, minus 10, 2, blah, 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 blah. To create this. Okay? So this shows you offset data.
Listen.
Yes.
Yeah. So, was asking that. Can you tell me more about the offset thing?
Offset tell where it is. If you have offset of 1, it put 1 cell above the diagonal cell. Make sense?
Okay.
If you use offset of minus 1, it put minus 1 cell below. Minus 1 cell above, so it's 1 cell below the diagonal tail. So offset tell where it is. So you know how to create. Then let's do Thomas method. So Thomas method is the same that we have. You watch the clock, right? So Thomas method, I have input matrix, okay? A, comma D. A has to be sparse matrix. If A is not sparse matrix, doesn't work. So I create the function that works just for sparse matrix. Okay, D equal to array shape n comma, and from A is equal to D where shape is n comma is as follows. So that's the code. So the code has C prime D prime, and then C prime D prime C prime 0 D prime 0 C prime I D prime I, and back calculate A, and done. You will use it. Okay, if you want to understand it from the code. It's the same as what you did in the homework, but that's you did in Excel, right? It's the same thing. So let's see how I use it. I do Thomas sp.spa.diax parenthesis A, comma D. So I put my matrix A and my matrix D. This is to solve Ax equal to D. So my A is that, A dot X is that, and A dot X minus D 0. So it worked. Done. Okay. Test function with other matrix A and B. So you can test it with other matrix. And this show you how to test it. You will go over it when you do the homework, right? These two dance, just change to dance. Okay, last but not least, linear algebra .sp solve. SP solve, okay. Look how I import it. I do scipy.spar import linear algebra. So this is linear algebra, but it's for spar matrix. So I do linear algebra.spar solve, SP solve. This solves spar matrix quickly, more efficient. Okay. If your matrix have many zeros, use this. Okay. And the answer is correct. So now let's talk about how to use spar matrix, because most of the time you don't do anything with dance. Spar matrix happen very frequent. Like for example, if you do partial differential equation 2D, if it is 1D, you may have just tridiagonal term. But if it's 2D diffusion problem, you may have tridiagonal and you may have other diagonal. Sometimes it become band, sometimes it have zero everywhere, but most of the time you have zero. So in that case, you should use spar solve. Okay. So let's talk about matrix in CSC spar matrix format, compressed spar column format or CSC. Attribute or something that you can call from this CSC matrix is .data, .indices, ID, indices pointer. Let's take a look. I have A3 already. You remember A3? A3 is just tridiagonal matrix. This is my A3. Okay. That is A3. 40 minus 1, 40 in the middle, minus 1 on the top, minus 20, minus 18, minus 16, minus 14, minus 12. On the top is minus 1, minus 2, minus 3, minus 4, minus 5.
What do we use dot to dance again?
If we have spar matrix, and if we want to see the full form in n by n form, you do this. If you just type A3 and shift enter, you don't see anything. Make sense? It doesn't show you anything. You just say, okay, spar at blah 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 blah. You don't know how it look like. So if you do .toDance, it shows what is the full form in the normal form. So that is A3 matrix. Have 40 in the middle, minus 1 on the top, minus 1, minus 2, minus 3, minus 4, minus 5, and minus 20, minus 18, minus 16, minus 14, minus 12 at the bottom. When I do A3.to CSC, it transforms into compressed spar column format. Okay? Compressed spar column format. I do .data, you give me everything. Give me 40, minus 20, 40, minus 1, blah, 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 blah. That's data, right? But this time, it's kind of strange. It doesn't like show in a particular form. When I do .indices, it just shows me 0, 1, 1, 0, 2, 2, 1, 3, 3, blah, 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 blah. Okay. Shape is have 16. So 16, 16. Data have shape of 16. Indices pointer shape has just 7. 1, 2, 3, 4, 5, 6, 7.
Professor,
Yes.
can you tell more about the CSC form?
No, we're not talking about that. Right now, I just tell you that CSC form has 3 attributes. 3 important attributes. Indices, index pointer, IND, PTR, and data. When you do it, it shows it like this. Okay? But what's that about? Okay. The data is a non-zero value in the spar matrix. So that is whatever we have. We have 40 minus 20, 40 minus 1, minus 18, 40 minus 2, minus 16. So that is the data, non-zero data that we put in. Okay. Indices tell the row that the data belong. So I have 0, 1, 1, 0 to 2. Okay. So 40 belong to row 0. Minus 20 belong to row 1. Another 40 belong to row 1. Minus 1 belong to row 0. Minus 18 belong to row 2. 40 belong to row 2. And so on. Okay? Good. Dot index pointer tells how to split the data before applying the row index. Okay. Let's see the shape. How many numbers do we have? We have 16 numbers. Okay, we have 16 numbers. How many indexes we have? Indexes we have. We have 16 indexes. What about this index pointer? Just 7. This tells me how it's split, I think. Okay. Okay. Index pointer tells how to split the data before applying the row index. And they have 0, 2, 5, 8, 11, 14, 16. Doesn't mean anything for me yet until I show the explanation. Okay, explanation. For the first column, look at A3 CSC dot index pointer. Okay. So, see, we have 0 to 2. First column pointer is 0 to 2. Start from 0 to 2, exclude 2. Use this index for the data. Okay. Pointer is just where do I start, where do I stop, or how I split. So when I say 0, 2, 5, 8, 11, so from 0 to 2, if I do A3 CSC data from 0 to 2 is 40 and minus 20. Okay. The row, corresponding row is dot indices 0 to 2. So it's row 0 and row 1. So that is column pointer. For this is for the first column. Okay, you see? So these two numbers is the range. The slide that is for the first column. This is for second column, third column, fourth column, fifth column, sixth column. How many columns do you have? Do you have 6 columns?
7 columns, 6 columns.
1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6 columns, 6 rows. So dot pointer, index pointer tells where do I start, where do I stop for column 1. So the number 40 and minus 20 is from 0 to 2, right? That is in column 1. So 1, 2, 3, 4, 5, 6. So I have 0 to 2, 2 to 5, 5 to 8, 8 to 11, 11 to 14, and 14 to 16. 1, 2, 3, 4, 5, 6. 6 comma. Okay? So dot pointer, dot index pointer, that tell me how to split. Okay? So with this method, it efficiently store the non-zero data. Okay? This is just to understand it. Do we need to memorize it? No. But if you have to look it up and understand how's that about, you need to be able to know it. Is this the only format? You have some other format. I explain you one. So when you use other format, you will understand it too. Okay? Column 0, I have 2. Column 1, I have 3 numbers. Why do I have 3 numbers in column 1? Because I have from 2 to 5. I have 2, 3, 4. Right? The data location 2, 3, 4 is in column 1. Alright? Span matrix solver, just linear algebra.st solve. but that has to be from scipy.sparse. Just solve it, get the answer, quick dot product also work. Then I can use
Wait,
Thomas algorithm. Yes.
what did he solve it for?
I have ax equal to b, or ax equal to d, or a3 multiplied by x equal to d3. My x is unknown, right? A is n by n matrix, which is known, given, but it's sparse, it's tridiagonal matrix. D is column vector, which is known. Unknown is x. So ax equal to d, I solve for x, I use Thomas algorithm. Thomas algorithm is going to be fast, faster than the rest because it's so specific. It works just for this case, other case it doesn't work. I can also solve as dense matrix, okay? Linear algebra that solve, but change it to dense first, A3 dot dense. Solve time comparison, you look at it for yourself. Thomas, 40 microseconds. Okay, this time, look at that carefully. Somehow, my algorithm takes 34.5 microseconds, sparse solver takes 52 microseconds. So somehow this time, mine is a little bit better, but I think it may not be a fair comparison because I may not put sparse solver into the function form. But somehow this one is faster, my method is fast. Okay. What about in the dense form? In the dense form, it's slower than solving in the sparse form. Okay? Solving in the dense form, not that fast. Not that SP-solve can solve any sparse matrix, but Thomas just solve tridiagonal matrix with the input in diagonal sparse format for it. Done. You need quiz, Daniel?
No, sir.
Did you pay attention to my lecture?
Yeah.
Just say yes. If you say otherwise, we have quiz.
I paid 100% attention.
Okay, let's do something.
Something wrong.
How do I fix this?
Just like straight line all the way.
Press tab, press tab.
That unconventional. I just labeled it wrong. I tried to do this. I'm seeing all the outside ones now.
Okay, without mouse, it still works. So we have 20 more minutes. Previously, you can solve system of linear equation. All the coefficient is just a constant. But life is not that easy, okay? Sometimes we have system of nonlinear equation. There are several methods to solve it. I show you one, Newton-Jacobian. I show you derivation, Jacobian matrix, scipy function, direct method without any automatic function, and using NumPy matrix, and use upscaling for large system. Derivation. You remember Newton method? Xn plus 1 equal to xn minus f at xn divided by f prime of xn. So this means you use the current point slope for the next case. Okay. Move xn to the left side. So you have xn plus 1 minus xn. And then multiply both sides by f prime. So this time you have f prime multiplied delta x equal to minus fx. That is 1D format. Right? One equation but unknown. 1D format. What if you have 20 equations, 20 unknown? We don't use slope anymore, but we use something close to slope, which is J, Jacobian. Okay, I don't know him, but we just use what he made. Okay, we use Jacobian. Delta x if you pay attention, it's a bold form. So delta x means delta x1, delta x2, delta x3, blah 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 to delta xn. Equal to minus f. Okay. That minus f is a bold form. So it's vector, right? So if you can calculate Jacobian matrix, okay, you calculate Jacobian matrix. Jacobian matrix will be what? N by n matrix, right? So delta x will be column vector, minus f will be column vector. So Jacobian matrix is just a coefficient matrix. So this means we have something like ax equal to b. We linearize it by using Jacobian. Now we have system of linear equation. We do kind of matrix inversion or Gaussian elimination or LU decomposition to get delta x, right? Then we get the next x value. So we start from initial value, which is x0. From x0 we can get x1. How do I get x1? When I have x0. So I have to calculate Jacobian matrix. How does it look like, Jacobian matrix? Ta-da! X, F, x1, 2, 3, 4, 5, till n. The subscript n over there is iteration n. xn plus 1, same thing but have subscript n plus 1 for the next iteration. F, n is fx, f1, f2, f3, f4, f5, to fn. At define iteration n. If we get the right x, f value will be 0 every component. Right? Jacobian matrix. I should put it in the exam. Okay, you need to memorize a little bit. J is n by n. Okay, we have df1. First row is just f1, second row f2, third row, last row n will be fn. So first column will be partial derivative with respect to x1, second column will be partial derivative with respect to x2, blah 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 until xn. So j is it's a slope, but it's slope from partial derivative. What will be j exactly? It's just a number. It's just a number, you know. What about minus f? Minus f defined at xn is just another number, a bunch of numbers. So basically you have ax equal to b. A is Jacobian. B is minus f. Minus f is just a bunch of numbers, just number. So we use what we have learned for system of linear equation, then we can get the unknown delta x. From the delta x, you start from x0, you can move to x1. And then if you keep doing that, you can do x2, x3, and 4. Got it? In what circumstances that we should use Newton-Jacobian? Of course, when we have system of nonlinear equation, or if you have black box. You have some black box model that you don't know what it is, but you know that it requires three unknown or maybe 4 unknown, and they give you the result. Okay, you can use Newton-Jacobian to solve this. Specifically, you remember previous homework that you did? You have 2 by 2 matrix raised to the power of 3 equal to 20, 30, 40, 50. You remember that? That can be solved by using Newton-Jacobian. Okay? That problem can be solved by Newton-Jacobian. And later on, I want you to do that. So that is the example of the black box. It has 4 input and it has 4 output. Can you do Jacobian matrix? Yes. So from Jacobian matrix, df1 by dx 1. So f1 is a function output, maybe top left or something. So when you do partial derivative, add epsilon in there. So we have y y at x plus epsilon minus y at x divided by epsilon. Limit epsilon approach 0, then we get the slope. That's a partial derivative. Okay. For the case where the function is well defined, not a black box, we can use Newton-Jacobian too. I'm creating the problem. I know the answer. The answer is x1 equal to 2, x2 equal to 3, x3 equal to minus 7. Okay. Equation 1, x1 squared plus x2 squared plus x3 squared. Equation 2, x2 minus x1 plus x3. Equation 3, just like that. Okay, now I have to create f1, f2, f3. What do? I move everything to the same side. I just move 62 to left hand side, move minus n to left hand side, move minus 31 to left hand side. Then I have f1, f2, f3. If my x is correct, then I get 0 everywhere. Okay. Initialize, we need initial guess. Okay. Okay. If you make the function by yourself and you want to debug, you want to know where's the bug, what you can do is you put the answer as the initial guess. Okay. And if you don't get the right answer, then you can identify where's the bug. Okay. The calculation step is we start with initial guess. Okay. Do and have for loop. Inside the for loop, we calculate Jacobian at a given x. How many times do we calculate Jacobian? As many as the number of iterations. We have to recalculate Jacobian every time because slope change with location, right? If you have in that case, you are in kind of 3D space. In every point in 3D, the slope cannot change. Okay, Jacobian change. After you calculate Jacobian, you have linear system instead of nonlinear. Then you solve j delta x equal to minus f. George, furthermore, which method shall I use to solve j delta x equal to minus f?
For non-linear or for linear?
It's a linear. Right now, once you do Jacobian, j is just a bunch of number. It's linear.
I guess you can use Gaussian elimination.
Gaussian elimination, okay. Any method works just fine. One thing that you have to be careful is that sometimes you may need partial pivoting. The diagonal term may be 0, you may need partial pivoting. Okay? Okay, once you solve it, you get delta x, you update x based on the delta x that you obtain. Check for convergence. There's two methods to check for convergence. Okay? Method 1, which I don't suggest because it's expensive, is substitute your x in here and check if left hand side equal to right hand side or not. In this case, it's not expensive. Okay? So if you substitute your x in and left hand side equal to right hand side, then you find the answer, right? That's one of the ways to check if you choose to stop your loop. Second method, which is cheaper, is to check if delta x is small enough. Okay? If your problem is dependent on how long does it take to calculate the function f. If it's quick, you can just substitute and calculate fs. If it's long, for example, you have some black box model, you have some f, you have f1, f2, f3, but you don't know what are those f, and it takes like 3 minutes. If it takes 3 minutes, or it takes maybe 5 seconds to calculate fx, you don't want to do option 2, you just do option 1, and you do option 2 at the very end. Okay? Get my point? It depends on how expensive it is. Alright. Convergence, order convergence. Newton-Jacobian is similar to Newton-Raphson. So it has quadratic convergence, okay, in general. So it's kind of 100 times faster than bisection or something, maybe 10. Is it 10 now? Order squared, delta h squared. It is faster, but if you actually do the calculation, you don't get 2, because this time you have multiple answers. Okay. Newton-Jacobian become Newton-Raphson as a number equation become 1. If you have one equation, Newton-Jacobian and Newton-Raphson are the same thing. Newton-Jacobian can take more iteration as number of equation increases. Okay? You have many unknown. You have more iteration. And same as Newton-Raphson, Newton-Jacobian doesn't always converge. Very often it doesn't converge. Okay? That's it. Done. Okay, now let's take a look. Okay, this one is 4 minutes. Okay, can we make it? So we try to solve what we have in presentation slide. I have two equations, same as before, and I use Newton-Jacobian. Okay, how do I do that? I have to calculate Jacobian, so I create Jacobian matrix. In Jacobian matrix, I have to do partial derivative. Okay. And I have to do partial derivative for every term. I use nested for loop. Loop I for row, loop j for column. Okay, and I have x plus. X plus is just x dot copy. X minus is just x dot copy. And x plus at a certain location is x plus at that location plus epsilon. X minus at a certain location is x minus the epsilon minus epsilon. So I do fi at x plus minus fi at x minus divided by 2 epsilon. So this is central scheme. Why do I do this? So you will later on go home and try to create Jacobian function by yourself, and eventually you will find that you have to do this, otherwise it doesn't work. Okay. Because every time, okay, the trick in this equation, Jacobian calculation is that in every loop, we reset x plus. So if we do d by dx2, every component has to be at the origin, just x2, that plus epsilon. See my point? If we do d by dx3, only x3 location that plus epsilon, the rest has to stay the same. So every time we reset x plus and x minus. And after we reset it, we say, okay, at location j, we add epsilon, and x minus at location j, we minus epsilon, then we can do the calculation. When we go to the next point, we reset again. That two line is for resetting. If you put these two lines outside, or you delete it from here, wrong. Okay. Once I do that, I get Jacobian matrix. So I'm ready to put it in the for loop. There's a SimPy. In SimPy, I can calculate Jacobian too. Okay. There's a Jacobian from SimPy, and they are the same. Believe me. You will check later on. And this is from SimPy. SimPy.div. Okay, I show you one by one. Oh, I have one more minute. Okay. Double check with direct SimPy function Pythonic way. Okay. SimPy have .Jacobian to calculate Jacobian matrix directly. That's from SimPy. Okay. Gaussian elimination. Use Gaussian elimination with partial pivoting to solve j delta x equal to minus f. I copy the whole thing from previously that I previously have, and then I put everything together. Okay, have a for loop. Bam! The result is done. 33 iteration and get to 3 minus 7. Okay, and this show calculation in each step, and it show solution with SciPy, which is the same. SciPy.f solve, but this time you have to put a bunch of equation in. Okay, so now we actually done system of that's speed comparison, nothing. Okay, error from verify, nothing. This is just a graph to show what you went error. So now we are checking convergence. Not that important, okay, but this show you like how it converges to the solution. Done. System of knowledge equation. And maybe 1 minute more. Okay. Thank you for coming. Do the homework. Submit the homework. Who haven't finished the homework? Just two of you. Come on, quick. Okay.
I'm done. I just need to.
Oh, you're done. After midnight, you get 0. Okay. Bye bye.